Assalamualaikum and good day to all of you. We are going to discuss Chapter 4, Higher Order Linear Differential Equations. Previously in Chapters 2 and 3, we discussed only on first order linear differential equations. So now we're going to discuss second order, third order, fourth order, and other higher order linear differential equations. Chapter 4.1 basically discuss on the preliminary theory of linear equations. The equations that we're going to discuss is only of linear type. Second order initial value problem. For the linear differential equation, the second order initial value problem has the following form. We are given a differential equation of second order, such as this one. In general, second order linear differential equation is given by a2 of x, y double prime, plus a1 of x, y prime, plus a0 of x, y equals to gx. Subject to two initial conditions, y of x naught equals to y naught, y prime of x naught equals to y1. So if we are given a differential equation of second order, and we are asked to solve the differential equation subject to these two initial conditions, the whole set of problem is known as the second order initial value problem. Example of a second order initial value problem. This is an equation of second order and this equation is linear. Y double prime plus 16y equals to 0. This equation is accompanied by two initial conditions. Y of 0 is equal to 2, y prime of 0 equals to negative 2. So if you are asked to solve a second order linear differential equation subject to these two initial conditions, so you can call this whole set of problem as a second order initial value problem. We can extend our understanding on the second order initial value problem to a third order initial value problem. 3y triple prime plus 5y double prime minus y prime plus 7y equal to 0. So this is a third order linear differential equation. And the equation is followed by three initial conditions. The example shown here, y1 equal to 0, y prime of 1 equal to 0, y double prime of 1 is equal to 0. So this is an example of a third order initial value problem. You notice that the number of initial conditions correspond to the order of the DE. If the DE is of second order, then there will be two initial conditions for a second order initial value problem. If the DE is of third order, then there will be three initial conditions for a third order initial value problem. In general, if we have an nth order initial value problem, we are asked to solve an nth order linear differential equation. So this is a differential equation of nth order because the highest order that precedes is n, and the equation is of course linear because y is the dependent variable. You notice that y prime, y double prime, the nth minus 1 derivative of y, the nth derivative of y, they are all to the power of 1, and the coefficients are all expressed in terms of the independent variable x. And you do not see any nonlinear function in y, and therefore we consider this equation as a linear differential equation and it is of nth order. So if you are asked to solve an nth order linear differential equation subject to certain conditions, subject to n number of initial conditions, so we call this as an nth order initial value problem. For the linear differential equation, we can identify it as being homogeneous or non-homogeneous. The equation is said to be homogeneous if the gx is equal to 0. The right hand side is equal to 0, the gx is equal to 0, and therefore this nth order linear differential equation is homogeneous. On the other hand, if the gx is not 0, then the nth order linear differential equation, though the gx is not 0, is said to be non-homogeneous. Examples. This is a second order homogeneous linear differential equation. Notice that y, y prime, y double prime, they are all to the power of 1. And the coefficient of y, y prime and y double prime, they are all expressed in terms of the independent variable x. And you do not see any non-linear function in terms of the dependent variable y, and therefore this equation is said to be linear. And the highest order that appears in this equation is 2, so this is a second order differential equation. At the same time, the gx is equal to 0. So we describe this equation as a second order homogeneous linear differential equation. If the right hand side is not 0, for example this cos x, which is the gx is not equal to 0, then we describe this equation as a second order non-homogeneous linear differential equation. Theorem 4.2 is on the superposition principle. Let me read this slide. Let y1, y2 until yn be n solutions of the homogeneous linear differential equation on an interval I. If c1, c2 until cn are arbitrary constants, then the linear combination y equal to c1 y1 plus c2 y2 plus cn yn is also a solution of the same differential equation on the interval I. Okay, let me explain what this theorem is all about. For simplicity, we are going to consider a second order homogeneous linear differential equation. Consider the second order homogeneous linear differential equation y double prime plus y equal to 0. Now at the moment we do not know yet, we haven't learned how to solve this second order homogeneous linear differential equation, but we are told that the solutions for the differential equation are y1 equals to cos x and y2 equal to sin x. By the superposition principle, it says that any linear combination of these solutions, such as y equals to 3 cos x plus 2 sin x, or y equals to minus 7 cos x plus square root of 5 sin x, is also a solution of the same differential equation. Therefore, the general solution of the differential equation is given by y equal to c1 y1 plus c2 y2 equals to c1 cos x plus c2 sin x. Using the same example, let me explain what it's all about. Given the solutions for the differential equation y double prime plus y equal to 0 are y1 equals to cos x and y2 equals to sin x. I would like to start by verifying that y1 is a solution of this dE. Okay, how do we verify that y1 is a solution of the dE? We are going to use the technique that we have learned in chapter 1. If y1 equals to cos x, then we shall start by differentiating y1 with respect to x twice, because the dE is of second order. So you find y1 prime, which is given by negative sin x, and y1 double prime, which is negative cos x. The next step is to substitute y1 and y1 double prime into the left hand side of the dE. Okay, so the left hand side is y double prime plus y. Now since we are using y1, so you write y1 double prime plus y1 Now substitute y1 double prime as negative cos x plus y1, which is cos x, and you get the sum of these two, the answer equal to 0, which is exactly the same as the right hand side. Now since the left hand side is equal to the right hand side, we conclude that y1 equals to cos x is indeed a solution of the DE. What about y2? Is it also a solution of the differential equation? Yes, you can apply the same procedure to verify that y2 equal to sin x is also a solution of the same differential equation. What you have to do is to simply differentiate y2 twice. Okay, you find y2 prime, y2 double prime, and then you substitute y2 double prime into this part of the left side of the equation, and then you substitute y2 into this part of the left side of the differential equation and get the sum of it, and you find out that the left hand side is equal to the right hand side. And so we say that this y2 equal to sin x is also a solution of the same differential equation. By the superposition principle, it says that if y1 is a solution of a DE, then any constant multiple of y1, that is c1y1, is also a solution of the same DE. What does this mean? We have seen that y1 equals to cos x is a solution of the differential equation. Now let us multiply y1 by any constant. Call it as a c1. In this example, I'm replacing c1 by a constant 3. Now, in fact, you can actually replace c1 by any constant that you like. You can substitute c1 by minus a half, or 100, or even square root of 6, for example. So c1 y1, in this case, is 3 times cos x. You will notice that c1 y1, or 3 cos x, is also a solution of the same DE. How do you verify? You substitute 3 cos x into this part of the left side of the equation, and then you differentiate it twice. Okay, differentiate this twice and substitute into this part of the differential equation, and you will notice that the left hand side is equal to 0, is the same as the right hand side. So we can conclude that 3 cos x is also a solution of the same differential equation. In other words, c1y1 is also a solution of the same DE. Regarding y2, if y2 is a solution of a DE, then the superposition principle says that any constant multiple of y2, that is c2y2, is also a solution of the same DE. Okay, so you have the function y2 found to be a solution of the DE. You multiply y2 by any constant that you like. Let's call that constant as c2. In this example, I have replaced c2 by the number 2. Okay, and 2 multiplied by y2, y2 is sin x, and I will find out that this product c2y2 is also a solution of the same differential equation. We can verify. You substitute 2 sin x into this part of the DE, and then you differentiate this twice and substitute into this part of the DE, and you find that the left hand side is equal to the right hand side. That means c2y2 is also a solution of the same DE. The next thing about the superposition principle is it says that any linear combination of y1 and y2, that is y equal to c1y1 plus c2y2, is also a solution of the same differential equation. In the previous example, we have discussed that if we multiply y1 by a constant, and if we multiply y2 by a constant, they are solutions of the same DE. Now, let us combine the two expressions together. So we have y equals to 3 cos x, or c1 y1. You add it with c2y2, 2 sin x, and you find out this whole expression here is also a solution of the same DE. Now try and substitute 3 cos x plus 2 sin x into this part of the equation, and then you differentiate this expression twice, substitute into this part of the equation, And you'll notice that the left hand side is equal to the right hand side. So that is the concept of the superposition principle. Let me repeat. By the superposition principle, it says that if y1 is a solution, any constant multiple of y1 is also a solution. That means c1y1 is also a solution of the same dE. If y2 is a solution, any constant multiple of y2 is also a solution. In other words, c2y2 is also a solution of the same dE. And then, by the superposition principle, it also says that the linear combination of these two, c1y1 plus c2y2, which in general we just call it as y, is also a solution of the same differential equation. If you look at the expression given in 7, you will see the expression y equal to c1y1 plus c2y2, which has a special name given to it. It is known as the general solution of the differential equation. In other words, for the differential equation y double prime plus y equal to 0, we can now form the general solution. The general solution is y equals to c1 cos x plus c2 sin x. Y equals to c1 y1 plus c2 y2. Okay, so this is the general solution of the given differential equation. Definition 4.1, linear dependence or linear independence. Let me read this slide. Two non-zero functions f1 of x and f2 of x are said to be linearly dependent on an interval I if one function is a constant multiple of the other for all values of x in that interval. That is, their ratio is a constant. Otherwise, they are said to be linearly independent on the interval I. Okay, let me summarize what's written in this slide. The slide says as follows. If you take the quotient of the two functions, in other words, you evaluate f1 over f2, and you find out that the quotient results in a constant, then you can conclude that f1 and f2 are linearly dependent functions. On the other hand, if you evaluate the quotient f1 over f2 and you find out that the result is not a constant, we conclude that the two functions f1 and f2 are linearly independent functions. So you have to get the ratio of the two functions to determine whether they are linearly dependent or linearly independent. When we say the ratio, it doesn't have to be f1 over f2 all the time. It can also be the other way around. You can write down f2 over f1 instead of f1 over f2. So if you calculate f2 over f1 and your result is a constant, you get the same conclusion, the two functions are linearly dependent. And if you evaluate f2 over f1 and the result is not a constant, you apply the same conclusion, the two functions are linearly independent. Here are some examples. Determine whether the functions f1 and f2 are linearly dependent or linearly independent on an interval I. Question number 1. f1 of x equals to 3x plus 9 and f2 of x equals to x plus 3. Now we like to find out whether these two functions are linearly dependent or linearly independent on a given interval I. What we have to do is to evaluate the ratio or the quotient of f1 over f2 or f2 over f1. So in my work here, I write down the quotient of f1 over f2. Now f1 is 3x plus 9 and f2 is x plus 3. Now once you have written down the ratio of the function f1 and f2, try to simplify whenever possible. In this example, you notice that the numerator has a common number 3. So let us take the number 3 out, and you notice that the numerator and the denominator now has a common factor that can be cancelled. So cancelling x plus 3, the result of the ratio is 3, which is just a constant. So since f1 over f2 is a constant, we conclude that f1 and f2 are linearly dependent on an interval I. Now if you evaluate f2 over f1 instead of f1 over f2, the result will be 1 over 3. So 1 over 3 is also a constant, so you will get the same conclusion: the two functions are linearly dependent. Example number 2. f1 of x is e to the x plus 4 and f2 of x is e to the power of 2x plus 8. We are going to take the quotient of f1 and f2. So here I take f1 divided by f2. f1 is e to the x plus 4 and f2 is e to the 2x plus 8. Since we have a division of two exponential functions with the same base, what we have to do is to take the power of the numerator minus the power of the denominator for the same base e. So you get e to the x plus 4 minus 2x plus 8. Okay, and then you have to simplify this expression. Open up the bracket, so we get e to the power of minus x minus 4, which of course is not a constant. How do you know it's not a constant? Because the answer involves an x. X is a variable. X can be any number within the interval I. So since x varies, therefore the answer is not a constant. If you take f2 over f1, your answer will be e to the power of x plus 4, which is also not a constant, and therefore we make the conclusion that f1 and f2 are linearly independent on an interval I. Example number 3. Example number 3, f1 is equal to ln x and f2 of x is equal to ln x squared. Taking f1 over f2, now f1 is equal to ln x and f2 is equal to ln x squared. Once we have written down the quotient, let us simplify whenever possible. Notice the denominator can be rewritten in the form of 2 ln x. We apply the law of logarithm. And we have a common function at the numerator and the denominator. Ln x appears at the numerator as well as the denominator, so you can cancel this ln x. And the result is a half, which is indeed a constant. So we conclude that f1 and f2 are linearly dependent on an interval I. Example number 4. f1 of x equal to sine 2x, f2 of x equal to sine x cos x. Taking the quotient of f1 over and f2, so f1 over f2 is sine 2x and f2 is sine x cos x. We know that by trigonometric identity, sine 2x is 2 sine x cos x. So sine x cos x at the numerator can be cancelled with the sine x cos x at the denominator. So the result is the number 2, which is just a constant. Therefore, we say that f1 and f2 are linearly dependent on an interval I. Number 5. f1 of x is e to the power of 3 ln x and f2 of x is 5x to the power of 4. Taking f1 over f2, we get e to the power of 3 ln x divided by 5x to the power of 4. This expression e to the 3 ln x is actually equivalent to x cubed. So when you take x cubed divided by 5x to the 4th, the answer is 1 over 5x. This expression here contains the variable x, where x is any number within the given interval I. And so we say 1 over 5x is not a constant. We conclude that f1 and f2 are linearly independent on an interval I. Okay, so those are some examples of how to determine whether two functions are linearly dependent or linearly independent on an interval I. The next discussion is on the Wronskian. Definition 4.3. Suppose each of the functions f1, f2 until fn are n minus 1 times differentiable. The determinant w, f1, f2 until fn is given by this form, where the primes denote derivatives, is called the Wronskian of the functions. Okay, to explain this, let me focus only, let's say, 4 functions, f1, f2, f3, and f4. So this determinant will be written as w, f1, f2, f3, f4. Now, since there are only 4 functions, then the determinant will contain a matrix of size 4 by 4, 4 rows and 4 columns. So the entries in the first row are f1, f2, f3, and f4. In the second row, you need to differentiate every function in the first row. So the entries are f1 prime, f2 prime, f3 prime, f4 prime. For the third row, you have to differentiate the functions in the second row. So what we have in the third row are f1 double prime, f2 double prime, f3 double prime, f4 double prime. And in the last row, we get the third derivative, f1 triple prime, f2 triple prime, f3 triple prime, f4 triple prime. For simplicity, let us focus only on 2 functions, f1 and f2. So how do we determine the Wronskian of f1 and f2? So we denote it as w, f1, f2. Since there are only 2 functions, so the determinant will be of size 2 by 2, 2 rows and 2 columns. So in the first row, the entries in the first row contains the functions f1 and f2. For the second row, you just have to differentiate each of the functions in the first row. So the entries in the second row are f1 prime and f2 prime. Now you all know, you have learned in your secondary school how to evaluate or how to find the determinant of a 2 by 2 matrix, of a matrix of size 2 by 2. Okay, let us recall. If we have a matrix of size 2 by 2 where the entries are written as A, B, C, D, so the determinant has the formula A multiplied by D minus B multiplied by C, AD minus BC. So we apply the same formula to evaluate the determinant, to evaluate the Wronskian of f1 and f2. f1 multiplied by f2 prime, so f1 multiplied by f2 prime minus f2 multiplied by f1 prime, f2 multiplied by f1 prime. So A times D minus B times C. Example. Compute the Wronskian of these 2 functions. Suppose f1 is e to the 3x and f2 is e to the minus 2x. So you write down w of the 2 functions that you want to evaluate is Wronskian. So you set up this determinant of size 2 by 2. The entries in the first row will of course be the functions given in the question. So this is the f1, this is the f2. To get the entries in the second row, you simply have to differentiate each of the functions in the first row. When you differentiate e to the 3x, we get 3e to the 3x. When you differentiate e to the minus 2x, you get negative 2e to the minus 2x. Then you evaluate the determinant, get the product of A times D minus the product of B, C. So A times D, e to the 3x multiplied by negative 2e to the minus 2x minus B times C, e to the minus 2x times 3e to the 3x. Now, when you get the product of these two, we get minus 2e to the power of x minus, and the product of these two will give 3e to the power of x, and the Wronskian is given by negative 5e to the power of x. Now, what is the use of this Wronskian? It can be used to check whether the functions are linearly independent. Let y1, y2 until yn be n solutions of the nth order homogeneous linear differential equation on an interval I. Then the set of solutions is linearly independent on I if and only if w of y1, y2 until yn is not 0 for every x in the interval I. Okay, what does this theorem actually say? It actually says that if you find out that the W or the Wronskian is not equal to 0, then you can make this conclusion. You can say that the set of solutions is linearly independent on I. On the other hand, if you know that the set of solutions is linearly independent on I, then W certainly will not be equal to 0. Again, for simplicity, we're going to focus only on two solutions. Let y1 and y2 be the two solutions of a second-order homogeneous linear differential equation on an interval I. Then y1 and y2 are linearly independent on I if and only if W of y1, y1 and y2 is not 0 for every x in the interval I. So in other words, if you want to test whether y1 and y2 are linearly independent or not, you just have to calculate the Wronskian of y1, y2 and check whether the result is not, and see that whether the result is 0 or not. If the result is not 0, then you conclude that the two solutions are linearly independent. Example 4.8. Suppose you have two functions. This is your y1. y1 equals e to the 2x cos x. This is another function, y2. y2 equals e to the 2x sin x. And we are told that they are both solutions of the homogeneous linear differential equation y double prime minus 4y prime plus 5y equal to 0 on the interval minus infinity to infinity. Okay, so we have already been told that they are solutions, so we don't have to verify that they are solutions. Use the Wronskian to verify that the above solutions are linearly independent on the interval. Okay, how do we want to use the Wronskian to verify that they are linearly independent? This is what we're going to do. Okay, so you didn't write down W of y1 and y2 because these are the two functions that you want to test is Wronskian. W e to the 2x cos x, e to the 2x sin x. Since there are only two functions y1 and y2, so you just have to set up a determinant of a matrix of size 2 by 2. There will be 2 rows and 2 columns. In the first row, you write down the two functions y1 and y2. In the second row, you just have to differentiate each of the function in the first row. So for this part here, I have to use product rule in order to differentiate e to the 2x cos x, u v prime plus v u prime. So I'll get this result. The same goes for this function here. I need to use product rule of differentiation in order to get this derivative. So u v prime plus v u prime. Right? Now once we are satisfied that our derivatives are correct, we can start evaluate the Wronskian. Or in other words, we can start evaluate the determinant of this matrix by using the formula A times D minus B times C. So A times D will be e to the 2x cos x multiplied by e to the 2x cos x plus 2e to the 2x sin x minus B times C. So e to the 2x sin x multiplied by negative e to the 2x sin x plus 2e to the 2x cos x. Okay, once we are done with this line here, we need to open up the bracket and simplify whenever possible. When we multiply the function outside here with the first term inside this bracket, we get e to the 4x cos square x plus, then multiply the function outside with the second term inside this bracket, we have 2e to the 4x sin x cos x. Multiply this function outside here with the one inside this bracket, we get plus, minus becomes plus, e to the 4x sine square x, and then you multiply the function outside here with the second term in this bracket, which is negative 2e to the 4x sine x cos x. And you notice that these two terms can be cancelled, and we are left with e to the 4x cos square x plus e to the 4x sine square x. Notice that these two have a common function e to the 4x, so we're going to factor e to the 4x. So what's left in the bracket will be the remaining function cos square x plus sine square x. But by trigonometric identity, cos squared x plus sine square x is equals to 1. So 1 multiplied by e to the 4x is e to the 4x, and we know that e to the 4x exponential function will never be 0. So since w is not 0, okay, by the theorem, we conclude that the two functions are linearly independent on minus infinity to infinity. Fundamental set of solutions. Let me read this slide. Any set y1, y2 until yn of n linearly independent solutions of an nth order linear differential equation on an interval I is said to be a fundamental set of solutions on the interval I. Thus, for a second order linear differential equation, if y1 and y2 are solutions and they are linearly independent, then they form a fundamental set of solutions of the differential equation on the interval I. Okay, so here we're going to look at the meaning of fundamental set of solutions. Suppose, for simplicity, I'm going to just focus only on second order linear differential equation. So suppose I have two functions, y1 and y2, and I found out that they are solutions, and I found out that they are linearly independent. So if these two criteria are met, they are solutions and they are linearly independent, then we conclude that they form a fundamental set of solutions of the given differential equation. Let us recall the examples. Let us recall the previous example. In the previous example, we have the functions y1 and y2. y1 equals to e to the 2x cos x and y2 equals e to the 2x sin x. We are told that they are solutions of this differential equation. And we have used the Wronskian to show that they are linearly independent. Okay, by using the Wronskian, we found out the Wronskian is not 0, w is not 0, and so we conclude that they are linearly independent. Now, since y1 and y2 are solutions and they are linearly independent, then we conclude that they form a fundamental set of solutions of the differential equation on the given interval. Now, since they have formed a fundamental set of solutions, we can now form the general solution. According to the superposition principle, if you can recall, if y1 is a solution, any constant multiple of y1 is also a solution. If y2 is a solution, any constant multiple of y2 is also a solution, and a linear combination of these is also a solution for the given differential equation. And this expression is known as a general solution. And therefore, for this particular example, since y1 and y2 form a fundamental set of solutions of the DE, the general solution is y equal to c1y1 plus c2y2, or y equal to c1 e to the 2x cos x plus c2 e to the 2x sin x. Okay, so that's all for today's lesson. Thank you for your attention. Assalamualaikum and bye.